All right, we're going to go ahead and get started. Today, we're going to be doing lecture 3. This is all going to be on transformations. And often what happens is you'll be given a question where you'll see that they give you a function, f of x. And then what they'll do with that function is they'll ask you for domain and range. They'll ask you for end behavior. They'll ask you for intercepts like x-intercepts and y-intercepts and all that stuff. And then they'll do a transformation of it so that f of x is going to turn into g of x, right? And f of x only becomes g of x once you transform it. So we're going to be learning about transformations today, what they are, how you get them, what they mean for the function as a part of analysis. So that's what we're going to be talking about today. Now, there are 3 main types of transformations. There are 3 types of transformations. Three main types of transformations we're going to talk about today. The first type is the translation. Translation. A translation is going to be a move to the up, to the down, to the left, and to the right. So this is moving a function. Moving a function. And it could be moving it up, down, left, and right. And we'll talk about all those today. The second type of transformation is called a dilation. Dilation. And this is where a function stretches, or shrinks. If you think about dilations, if you're in geometry class, maybe they'll tell you that 2 figures are similar, which means they're of the same shape, but one shape will be bigger than the other. That's what I'm talking about with dilations. When we're talking about dilations, something can grow or something can shrink. And that's what we're going to be talking about a little bit later. And then the third type of transformation is called a reflection. Reflection. And I'm pretty sure you know what a reflection is. If you reflect something, that means you're flipping it over an axis. So you could flip something over the x-axis, or you could flip something over the y-axis, And we'll talk about both of those types today. Okay, so those are the 3 types of transformations. And if you look at this picture down here that I have a triangle right here. And what I'm doing with this triangle right here is I am flipping it over the x-axis. So this triangle gets flipped over the x-axis. That's called a reflection. So this triangle is being reflected over the x-axis. And then what happens is it's not flipped over, it's just moved. It's just moved over here. And remember, that's called a translation. That's when you move something up, down, or left or right. So there's a reflection that occurs, and then there's a translation that occurs. But notice the triangle is still the same size, right? So it's not like it's been dilated or stretched or shrinked. The triangle is still the same size. All I'm doing is I'm reflecting it first, and then I'm translating it over here. So that's the difference between translations and reflections. Okay, so I'll leave this up there for a little while longer, and then we'll move on and we'll talk about the first type, translations. So often what will happen is they'll give you a function f of x, and then they'll give you its transformation g of x. Maybe they reflected the function over the x-axis, and g of x is going to be the result. And they'll ask, what is the domain and range of this function now that it's reflected over the x-axis? So that's a common type of question that you'll see on the SOL test. Okay, let's move on to the next slide. Okay, so let's talk about translations. Translations. Okay, so typically when you go up, what you're doing is you're adding a number to the function. So if I start off with f of x and I add c on the outside, that is called moving up by c. So this is moving up by c. So if I have to add a number to move up, then I have to subtract a number to move down. So if I have f of x minus c, that would be the formula for going down by c. So that's the way you think about moving something up and moving something down. But over here in this picture, notice that we're moving to the right. We're moving to the right. So it's not like we're moving up or down. We're actually either going to the left or the right, at least in this picture. So let's talk about those. Now, this is on the outside, right? If you add something on the outside, that means you're going up. But what if you were to add inside the parentheses? That's what we're going to do next. So let's say you add on the inside. Let's say I have f of x plus c, right? I'm adding on the inside of the parentheses, so this is going to move it to the left by c. This is going to move it to the left by c. So if you add on the inside, now you're starting to move to the left. And if you want to move to the right, then you have to do the opposite. You have to subtract on the inside. Subtract on the inside. And once you do that, that means you're going to the right. That means you're going to the right. So a lot of kids get confused when you're talking about moving left, because they think that if you're moving left, you're subtracting, but that's actually not true. If you add on the inside, you move to the left. But if you subtract on the inside, you're moving to the right. And I think that trips a lot of kids up. They think, well, if you want to move to the right, shouldn't you be adding? No, that's actually not the case. If you subtract on the inside, you move to the right. And if you add on the inside, you're moving left. So this is correct. So that's translations. So to move this triangle over here to the right, what I'm doing is I am subtracting on the inside. So I have f of x minus c, moving c points to the right. So that is translations. You can move up, down, or left and right. Okay, now let's do dilations. Dilations. Okay, so we're not going to be adding or subtracting this time. We're actually going to be multiplying by a number. So if you multiply f by a number, like let's say c, if you multiply by c, that's going to be a vertical stretch. That's going to be a vertical stretch by a factor of c. And this is true if c is greater than 1. Only if c is greater than 1. So if I was to take f of x and I was to multiply it by 4 on the outside, that means I'm taking the function and I'm stretching it by a factor of 4 vertically. So that would be a vertical stretch by 4. Okay. Now, what happens if C is less than 1? That's what we're going to talk about next. Vertical stretch by a factor of C. It would be a vertical shrink. It would be a vertical shrink by a factor of C. By a factor of C if C is between 0 and 1. Only if C is between 0 and 1. Okay? So that's the difference between a vertical stretch and a vertical shrink. It's the number that we're multiplying f of x by. Now, we multiplied by 4 this time, but let's say we multiply by 1/2. What would that mean? Well, 1/2 is between 0 and 1, right? So this would be a vertical shrink by a factor of 1/2. This would be a vertical shrink by a factor of 1/2. While this one over here, we're multiplying by 4, so that would be a vertical stretch. It's all based on how big the number is out in front. If it's greater than 1, it's going to be a vertical stretch, right? It's like you're taking the function and you're grabbing it and you're stretching it in the vertical direction. But if your number is less than 1, like let's say it's some kind of fraction that's between 0 and 1, that would be a vertical shrink. That's like grabbing the function and shrinking it down vertically. And we'll take a look at what that looks like when we get to the problem sets. Now, here's a very important note that you want to keep in mind. So I'll put this in blue. Put a star beside this because I think this is very important. It's important to know that, well, let me just write note. It's very important to know that a vertical stretch is the same thing as a horizontal shrink. As a horizontal shrink. Okay? A vertical stretch is actually the same thing as a horizontal shrink. Really think about that. Okay? Now, I want you to imagine grabbing a function like, let's say, x squared. Let's say you grab that parabola and you stretch it in the vertical direction. Well, if you stretch that function in the vertical direction, you're grabbing it and you're stretching it up and down, right? You're stretching it in the vertical direction. Wouldn't that be the same thing as horizontally shrinking it, right? They're the same thing. A vertical stretch is a horizontal shrink, and then vice versa, right? You could do it the other way. A vertical shrink is the same thing as a horizontal stretch. So they're kind of opposites in that way. A vertical stretch is the exact same thing as a horizontal shrink. So I'll just leave you with that. Okay. So that is dilations. You're actually multiplying f of x by a number c. Okay? Now, what if that number is negative? We haven't talked about that yet, have we? What if we multiply by a -3 on the outside? Well, that's going to be a reflection, actually. So let's talk about that on the next slide. Reflections. This is the third type of transformation that we're going to talk about today, a reflection. So how do you reflect a function over the x-axis? Well, if you multiply by a negative number, like let's just say it's negative f of x, then this is going to be a reflection over the x-axis. Well, we say reflection about the x-axis. So if you put the negative on the outside, you're reflecting over the x-axis, okay? And if the negative is on the inside, like this, f of negative x, then that's going to be a reflection about the y-axis. That's going to be a reflection about the y-axis. And when I say about, that just means reflection over. So if the negative on the outside, we're flipping the function over the x-axis. Okay. But if the negative is on the inside, we're flipping it over the y-axis. So that's the difference between the two that you need to know. And yes, I will take off if you put the wrong axis down, because that's important. Okay, so those are the three basic types of transformations. So going back, we talked about translations. You're either adding or subtracting. If you do it on the outside, you're going up and down. If you do it on the inside, you're going to the left and the right. Dilations, that's when you multiply by a number. Vertical stretch if it's a big number. Vertical shrink if it's a smaller number. And then reflections are going to be when you multiply by a negative number. You're going to reflect about the x-axis if it's on the outside like this. But if it's on the inside like this, you're reflecting over the y-axis. Okay, so let's take a look at some problem sets that I wanted to do. Let's take a look at a couple examples, and hopefully this will help illustrate my point. Let's do number one together. And for all of these questions, we're going to be naming two things. We're going to be naming the parent function. We want to know what the parent function is. And number two, we want to know what the transformation is. What is the transformation? Okay, so let's do f of x equals absolute value of x plus 3. What is the parent function and what is the transformation? So for this one, we have the absolute value function. So we know that this is the absolute value function. Absolute value function. That's the parent function. And I know that because it has these absolute value symbols around the x. But what is the transformation? What's going on here? Well, since we're adding 3 on the outside, that means we're moving up 3. That means we're moving up 3. So I want to take a look at Desmos to see what that looks like. Okay, so on here, I want to graph the parent function first. So let's graph f of x equals the absolute value of x. And I'll be using ABS to stand for absolute value. So that's absolute value. I'll move it right here so you can see it a little bit better. You get that classic V shape. Now what I want to do is I want to graph the function that we're given. G of x equals the absolute value of x, but I'm going to add 3 on the outside. So notice what happens. We start off with the blue function, and then we end up at the green function. The only thing that's changed about the function is it's being moved up by 3. That's really the only thing that's changed. So this transformation is going to be up 3. That's the answer. Let's try the second one. F of x equals square root of x minus 4. Square root of x minus 4. So what's the parent function here? What would be the simplest function for this? Well, it would be square root of x, right? P of x equals square root of x. That's going to be the square root function. The square root function. Now, when you graph it, and I'll show you how to do this in a minute, when you graph it, you'll get the square root graph. But I want to know what the transformation is. What's going on here? Well, we're subtracting 4 on the inside, right? And if we add or subtract on the inside, that means we're either moving to the left or to the right. Now remember, if we're adding, we're moving to the left. But if we're subtracting, like we're doing right here, we are moving to the right. So we are moving to the right by 4. For this one, we are moving to the right by 4. Okay? So let's go ahead and take a look at that on Desmos to see what it would look like. We're going to graph the parent function, and we're going to graph the function that we're given. So let's take a look at that. I'm going to let f of x be square root of x. And the shortcut for this is sqrt, square root. So that's the square root right there, that blue function right there. That's the square root graph. And now what I want to do is I want to graph the function that we were given. So I'm going to graph g of x equals square root of x minus 4. Okay? Do you see the difference between the blue graph and the purple graph? The blue graph starts at 0, 0, but the purple graph is starting at 4, 0. That means it moved to the right by 4. So that's what I mean by moving right. We're subtracting on the inside, not on the outside, right? On the inside. That's going to move it to the right. And if this negative 4 was on the outside, like let's say it was on the outside like this, then we would be moving down since we're adding or subtracting on the outside. So that's the difference between the parent function and the function that we were given. We're actually moving to the right 4 because we're subtracting 4 on the inside. Okay? Let's take a look at number 3. Let's say we're given f of x equals 4x squared. 4x squared. What is the parent function? P of x. You can write out the formula or the name. And what is the transformation that's happening with this function? So let's take a look at that. What's the parent function? Well, the highest exponent is 2. So this is going to be p of x equals x squared. This is the quadratic function. The quadratic function. This is going to be that U-shaped graph. It's going to kind of look like this, right? It's going to have that U shape to it. Not the V shape that's characteristic of absolute value, but the quadratic function. Okay? So what's going on to make P of x change to F of x? Well, we're multiplying by 4, right? And if we're multiplying by 4, that means we're vertically stretching the function. So this is going to be a vertical stretch. A vertical stretch by a factor of 4. By a factor of 4. So let's take a look at that. What is this going to look like when we stretch it by a factor of 4? Well, if we go to Desmos and we graph the parent function, p of x equals x squared, we're going to get the standard U-shaped graph that starts at 0, 0 as the vertex. Okay? And then f of x is going to be the new function. We're going to multiply by 4 and see what happens. So do you see the difference? We start off with the black function. That's our parent function. The simplest form of all quadratic functions, right? That U shape. But then this red function is taking the black function and stretching it vertically by 4. So see the difference? This graph is much skinnier. It's more narrow. It's more vertically stretched than the black function. Okay? So that's what a vertical stretch is going to look like. So let's head on back to the slide and let's do number 4. All right. Let's say we're given f of x equals, let's say we're given 1/2 x squared. What would that be? Well, the parent function is still p of x equals x squared. It's still the quadratic function. That has not changed, right? Quadratic function. it's still going to give you that U-shaped graph since it's x squared. But we're multiplying on the outside by 1/2. So what would that be? That would be a vertical shrink. A vertical shrink by a factor of 1/2. By a factor of 1/2. So what would that look like? Imagine taking f of x equals x squared, this parent function right here, and you're grabbing it and you're shrinking it vertically. So you're not stretching it, you are in fact compressing it. Let's see what that would look like. Okay, so we're on Desmos, and the only thing I'm going to change is I'm going to change the number out in front to be 1/2. So notice the difference now. We're starting off with the black function, and then we grab that black function and we compress it vertically. We shrink it down vertically, and then we get this red function. This graph is more horizontally stretched, I would say. But remember, horizontal stretches are the same thing as vertical shrinks. So we vertically shrunk it down by a factor of 1/2. So now we get this wider graph than we started off with. Okay, so that is vertical stretches and vertical shrinks. And then the last ones we want to talk about are reflections. So that was number 4. So let's do number 5 over here. Number 5. Let's say we're given f of x equals, let's say we're given -2 to the x power. -2 to the x power. So this is the function that we're given, -2 to the x power. What's the parent function and what's the transformation? Well, the parent function is going to be the exponential function. P of x equals 2 to the x power, also known as the exponential function. This is much different than the last one that we were talking about. This function is going to look like this. It's going to have a horizontal asymptote down here that the graph never crosses. Okay, so that's basically what it's going to look like. And what we're doing with this is we're multiplying it on the outside by a negative. Well, I guess it would be more accurate to say -1. We're multiplying it by -1 basically. So what does that mean? Well, since the negative is on the outside, that means that we're reflection about the x-axis. So what's going to happen is, let's assume that this is the x-axis. If we were to flip this over the x-axis, it would look more like this. It would look more like that, since we're reflecting it over the x-axis. So let's take a look on Desmos at what that would look like. Let me get rid of this. Okay, so let's say the parent function p of x was 2 to the x power, 2 raised to the x power. And we get our familiar exponential growth graph. That's the blue graph. Notice that it has a horizontal asymptote on the x-axis, so it never actually crosses the x-axis. It just gets closer and closer, infinitely closer, right? Now, what we're going to do is we're going to multiply on the outside by a -1. So that's going to be a -2 to the x power. And now notice the blue graph has changed into the green graph. Notice that the function has flipped over the x-axis. Okay. So that's what that's going to look like. That's called a reflection. And then lastly, let's do this one. G of x equals 2 to the negative x power. 2 to the negative x power. What would that look like? Well, it's still an exponential function, right? So we're still starting off with p of x equals 2 to the x power, the exponential function. But are we reflecting over the x-axis or are we reflecting over the y-axis? Well, since the negative is actually with the x this time, this is a reflection about the y-axis. So this is totally different, right? This is going to be a reflection about the y-axis. So now let's take a look at what this is going to look like. Let's go on back to our graphing calculator, and this time I'm going to get rid of the negative out in front, and I'm going to put the negative on the x. Okay. Now, do you see the difference between the blue function and the green function? The blue function has been flipped over the y-axis. So now you see exponential decay. This is an exponential decay, right? So if you take a look at the green graph, it's still an exponential function, right? It still has that exponential shape. It still has a horizontal asymptote on the x-axis, but it's been flipped over the y-axis. So now, instead of being exponential growth, this is a model of exponential decay, since the function decays over time. Okay, so that is a reflection over the y-axis. So let's talk about